Okay, so welcome everyone to the Kadanoff seminar. Today we're very happy to have Andrea Dei from Harvard University, and who'll be telling us about string correlators in AdS3.
So hello to everyone. I'm really happy to be here, and I'm looking forward to joining you in September. And today I'm going to present a series of works done in collaboration with Lorenz Eberhardt, and the latest one appeared actually this morning. And the common story is that, so I will describe how to compute string correlators on AdS3 and how much this can teach us about the dual CFT. So let me start with some motivation. So I'm interested on string theory on AdS space in view of holography. And one of the nicest setups is AdS3 with pure NSNS flux, because in this case, we know what the worldsheet CFT is, and it's the so-called SL2R Vezzumino-Witten model. So you might have heard before of the SU2 Vezzumino-Witten model. This is the non-compact cousin of it. Now, this model is believed to be completely solvable. So we might really have access to many string theory observables, but it's just believed to be solvable, but hasn't yet been solved as a 2D CFT. And in particular, we have a very good control on the spectrum. So we know what the spectrum of this 2D CFT is from since many years, but we have less understanding of what the correlators look like. And the main difficulty, or if you are an optimistic, you would call novelty or feature of AdS3 at pure NSNS flux is the so-called spectral flow. Now, let me try to introduce this concept through a cartoon that to experts might sound a bit silly, but I really want to have on board everyone, also those that never heard these words before. So we will compute correlators on Euclidean AdS3. So let me think of AdS3 not as a cylinder, but as a sphere. And this is the ball that you see on the slide. And the external surface of this ball is where the boundary CFT lives, and the internal part of the ball is our AdS3 space. And you see there is this bluish surface. This is the worldsheet of the string. And the worldsheet is attached to the boundary at 4 points. So these are kind of our asymptotic states. So indeed, these are, you should look at these 4 regions as the vertex operators that we are computing correlators of. So this is the cartoon of a 4-point function, if you want. And if you zoom close to the insertion point, you see that there are multiple sheets close to the insertion point. So the worldsheet can wind multiple times around the insertion point on the boundary. And this is what this cartoon tries to convey. This would be the spectral flow. So there is a non-negative integer that labels different vertex operator we insert in correlation functions. And this is the source of many technical difficulties in computing these correlators. And indeed, very few results exist in the literature, at least before what I'm going to present, to the point that not even the 3-point function where all 3 vertex operators have 1 unit of spectral flow is known in closed form. But by the end of the talk, I will present a formula that is a closed formula for arbitrary amount of spectral flow for 3- and 4-point functions, and all parameters will be generic. Now, the outline of the talk is the following. So I will start with some introduction. And in this introduction, I will introduce to you the protagonists of the game, meaning the vertex operators entering the correlation function. And there will be a couple of slides of math, but it will be very hands-on math, so don't be worried. And then we will be ready to come to the meat of the talk, which is how we compute these correlators and what the formula for these 3- and 4-point functions looks like. And then we can get the reward of this, because we can start analyzing the analytic structure of the answer that we get, see where we have what we can learn from this, and check whether this matches or not proposals for the boundary CFT. And I will conclude with some questions. Okay, I want to be a bit more precise on what is the setup. So far I was a bit sketchy. So we will compute these correlators in bosonic string theory at genus 0, so we don't have yet a supersymmetric version of this, but the bosonic story should already capture a lot of physics. And everything I will say is just a consequence of symmetries, so we are just trying to list all the symmetries of the model and turn them into clear equations and solve them simultaneously. And in particular, the symmetry that will play a dominant role is the symmetry algebra of this 2D CFT on the worldsheet, the SL2R Bezzomino-Witten model, and these are the commutation relations. Now, it's not important that you memorize the exact form of the commutation relations, but remember we have three currents that I denote by J, and we have a J plus, a J minus, and a J3. And essentially all the computations I'm going to present are just a consequence of these commutation relations. Okay, now we come to the vertex operators. So let me start from the easiest ones, which are those where we have no spectral flow. And the fact that we have no spectral flow is denoted by this big zero that you have on top. And then you have the usual dependence on the worldsheet coordinate. So this is where you insert your string operator on the worldsheet. So this is denoted by the coordinate z. But we also have another coordinate, which is denoted by x, and is a coordinate on the boundary. So this is a coordinate on the boundary, and in the cartoon that I was presenting before is the point on the boundary where the worldsheet is attached. Okay, so if I go a few slides back, so these 4 points on the boundary I will denote by x1, x2, x3, x4. So that's the meaning of the x variable. I mean, there is of course a more technical definition, but that's how you should think of it. And then of course we need some label to take into account the different representations that we have. So this will be the SL2R spin label. And for all these vertex operators, we know explicitly what is the OPE of the currents of our symmetry algebra with these vertex operators. And you see that they are relatively nice. We just have simple poles. Now, the situation is a bit more intricate when we do have this spectral flow. So first, the 0 is now replaced by W, which is a generic non-negative integer, and denotes how much spectral flow we have. Again, we have a worldsheet coordinate and the boundary coordinate as before. And again, we have the SL2R spin. But now we have an additional parameter that was not around for the unflowed guys. And this is the J30 eigenvalue that is interpreted as the space-time conformal weight. Now, if you think a bit of it, it's natural that since we have two coordinates, x and z, on the boundary and on the worldsheet, we want also to know how fields transform with respect to these two coordinates. So we need two labels to take into account conformal weight in these two spaces. So conformal weight on the worldsheet and on the boundary. So it's natural that we have two labels, J and H, and it just happens that when we have zero spectral flow, they are the same thing, they coincide. Also in this case, you can write down OPs. They are known explicitly in closed form, but I didn't want to put them on the slide because they are ugly and we have many higher order poles. So we have poles up to order W or W-1, something like this. So it's a bit more intricate. We have an extra label H and we have higher order poles. And now comes the math part. So for the following, I will need to quickly review what I mean by branch cover or covering map. So this is a map from the sphere to itself, which is holomorphic and has finitely many ramification points. And practically speaking, this will mean for me that I will assume the following, that a covering map has the following Taylor expansion. So I have some ramification points Zi that I map to some image xi, and then close to these Zi ramification points, I have this Taylor expansion, and notice that for a generic W, so imagine W is something like 10, say, you have many missing Taylor coefficients here, Okay, so all the Taylor coefficients until order W, they are missing in this expansion. Now, you see that this map in this hands-on definition is defined by the choice of this Zi on the base space, their images Xi on the covering, and the choice of these ramification indices, Wi. Now, if you choose at will these parameters freely, for generic choices, you won't find such a map. So in order for this map to exist, you need to satisfy some relations. The Xi's and Zi's should be related. And we will see a very concrete example of this in a moment. Another formula that I will need is computing the degree of the covering map. So we are covering the sphere, but how many times? 2 times, or we are going around 3 times? So this just follows from this Riemann-Hurwitz formula. You just need to sum these Wi ramification indices with some shift. So you can just compute from your choice of Wi's. So let's make an example to be more familiar with this and not be scared by this math. So let's find the covering map that has ramification indices 2, 2, 1, and 1. Now, let me choose my points to sit at 0, 1, and infinity, both in the base space and in the cover. And then I will have some residual dependence on their cross ratio. Now, if you, from the Riemann-Hurwitz formula of before, I can compute the degree of the map. Just need to sum this 2, 2, 1, 1 with some shift, and I find that the degree of the map is 2. So it has to be a ratio of polynomials, and the fact that the degree is 2 tells me that the numerator we have degree 2. Then I also know that at infinity, which is the third point, is going linearly. So I know that the Taylor expansion of gamma of zeta will go as zeta for zeta close to infinity. So this means that the denominator has to be a polynomial of degree 1. So that's my ansatz for the covering map, and I have 4 free parameters. Now, I can be very naive at this and just impose the Taylor expansion I was writing before. And since at 0 and 1 we have spectral flow 2, this means that, oh, of course, okay, we need to map 0 to 0, and 1 to 1. This is the choice we made here. And then since we have spectral flow 2 in each of these, the first Taylor coefficient at 0 and at 1 should be 0. Now, if you do this game and impose these 4 constraints for your 4 free parameters, you find a unique answer. Okay, and this is the covering map that you find. So we know how to find these maps, at least in simple examples. But now you should complain, because I have 4 points and I have imposed the Taylor expansion at infinity, at 0 and 1, but I also have z. So I should impose the Taylor expansion at z, which is saying that gamma of z should be x. So z should be mapped to x. But I have no longer any free parameter. So either z and x are related, or there is no map that does this. And indeed, now what you can do is recast the requirement that gamma of z is equal to x in the form of a polynomial. So I'm just saying that for here being z equal to x, you just raise this here, and you rewrite the whole as a polynomial. So you can define this polynomial, which I call P2211, which are the ramification indices we chose, and it depends on x and z. And when this polynomial is 0, then the 2 x and z are related and the covering map does exist. If it's not 0, there is no covering map. So this polynomial encapsulates the existence of a covering map. There is a question.
Does the polynomial that results not depend on the first 3 choices that you made, or are those just like choices that we'll continue to make?
So the final answer that we find, this gamma of z solution, gamma of zeta, does depend on the choice of 0 and 1, because we ask that gamma of 0 is 0. So generically, I should ask that gamma of zeta I is xi, and then enough many Taylor coefficients are vanishing until order wi. So it depends, but in not a fundamental way. Okay, so we have this polynomial, and I guess now I might have convinced you that you can repeat the process for other choices of the ramification indices. So in general, I can define this polynomial also in other cases.
So how does this polynomial depend on the choices of the W's? Can you say things about how the order of the polynomial is a function of?
Yes, I mean, I don't remember by heart, but we have, yeah.
I mean, roughly how nasty is it getting as you grow the W's?
It's a linear combination of the W's. The order, so yeah, I think something like this. I don't remember by heart, but we know this. And actually it's important because that's how you realize that this is the structure behind. So, okay, you can define these polynomials also for other choices of ramification indices, and there are actually algorithms which are more efficient than what I described. So we have control on this kind of polynomials. Okay, now we come to the meat, and we are done with the math part. So the strategy in computing these correlators, as I said before, is just listing all the symmetries that we know the model has and trying to solve them simultaneously. So we have global symmetries. By this I mean global world identities, but we also have actually affine symmetry. We have the whole tower of currents. And then we will also use the so-called Knitzit-Zamolodchikov equation. Don't be scared by the long name. I will quickly review what this means. And in some cases, we also have some states that are actually the zero state. So when inserted into a correlation function, they will force the correlation function to vanish, and this will give extra constraints. Now, what we are doing is to write explicitly these constraints for explicit choices of the W's. So say we take the values of the spectral flow parameters to be 1, 1, 2, 2, for example, and we can write explicitly all these constraints and try to solve them simultaneously. What we cannot do is write these constraints in closed form as a function of W. Okay, so some of these constraints are not known in closed form as a function of W. So all we can do is to do many, many examples and try to deduce from this the general structure of the solution. But what we get from this analysis, and this is, if you want, the take-home message, is that once every property of the correlator with no spectral flow, the one that has been deeply studied in the literature by Teschner, Maldacino, Gur, and many people, once you have control over this correlator, any property you can translate into the corresponding property of the correlator with spectral flow, because the formula I will present will turn one information into the other one. Okay, let me start to list the various symmetries and see what they imply. So global world identities are probably the easiest. They just allow us to fix 3 insertion points on the worldsheet and on the boundary to be 0, 1, and infinity. And then if we analyze 4-point functions, we have 1 residual cross ratio on the boundary and on the worldsheet. But affine symmetry is much more than this, right? We have all the modes. We had these J plus or minus or 3n currents, and these imply actually more constraints on correlators. And so it was realized 3 years ago that, okay, yes, it's true that these OPs are ugly and you have higher order poles. You see that the sum runs up to W plus 1, the sum in the first line, so you have many poles. But there is a nice combination, the one in the last line here, that is very, very regular. So it goes like zeta minus z at W minus 1. So this means that if I insert this equality into a correlation function, on the one hand, I can compute the correlation functions by taking OPEs of J minus, J3, and J plus. On the other hand, I know that it's very regular, so I can require that the first W minus 1 Taylor coefficients are 0. And this will give me a system of equations, and these are the constraints that follow from affine symmetry, that affine symmetry is imposing on my correlators. So the good news is that we know how to translate affine symmetry into concrete equations that constrain correlators. The bad news is that they are a mess. So this is an example where all vertex operators have spectral flow 1. So the higher the spectral flow, the longer these equations get. And the difficulty is that they are at the same time differential equations. So you see that we have derivatives in xi, but they are also recursion relations in the hi's. So you see that here we have h1, that's h1 minus 1, so it's down by 1. Here nothing is shifted, and here someone else different from h1 is shifted up. So they're both differential recursion relations or something like this. So these are hard to solve. But we found a good change of variables that gives us handle on these equations. So we are essentially introducing a integral transform. Okay, so we trade the variable h for a continuous variable y. So now our vertex operator do not depend only on x and z, but there is also a y. And this has the advantage that turns recursion relations into differential equations. And this is an example of what the constraint on the previous slide turns into.
Prior to this, h was discrete or continuous?
So h minus h bar is discrete, but h plus h bar is continuous. And
But that same property is not true on the right-hand side. Yeah?
so
Like
if
h
you-
minus the spin can become continuous in the right-hand side, yeah?
So in the right-hand side, the y takes values on the sphere, so it's a complex parameter. Maybe what you would like to see is the inverse of this transform, and that is a sum over h minus h bar being discrete and an integral over h plus h bar being continuous. So there is this property, but you just see the inverse of this transform. Now you might say, okay, it doesn't look much nicer than the other equation. It's still a PDE, and you have one of these for each vertex operator. So in a 4-point function, we have a system of 4 of these equations, but they are linear. They are linear PDEs, so if you fight enough with Mathematica, you get to solve in various examples.
Does the y variable have a direct physical interpretation?
Not that we know of.
Because there's all this recent work on analytically continuing in spin and things like that. I wonder if...
Yeah, I don't know, but we didn't find. And indeed, the final answer we want to go back and in h variables because we understand much more of the physics. At the moment, it's for us a tool to solve the equations. Now, I was saying that you get a system of these linear PDEs that we are actually able to solve in many examples. And if you stare at this mess, you might say, okay, the solution will be just very long and ugly, but it's actually not. And it has features that we didn't know of and we still cannot explain, but just stare at. So the solution that we find is the following. And it's the one on the red box. And let me try to introduce it to underline an analogy that the formula that we find has with ordinary 2D CFT. So if instead of solving constraints from the affine symmetry, you look at constraints of the global world identities, and not for the correlator with spectral flow, but for the correlator with no spectral flow, you would say that the dependence on xi and xj is just the usual one in CFT, right? Where you have x1 minus x2 raised to some conformal dimension that here is played by the ji's. And then you have some unknown function of the cross ratio. And here by x1 minus x2 in the top formula, I mean x1 minus x2 and x1 minus x3. So that's the usual formula you find on CFT books, chapter 2 or 3. Now, the solution that we find that we are solving not global symmetries, but affine symmetry constraints, and not for zero spectral flow, but for flow, generic spectral flow, has a very similar structure. So you have to replace the ordinary differences, x1 minus x2, etc., by what we call generalized differences, and are actually functions of x, z, the two cross ratios, and of the auxiliary variables yi, yj. But then the form is very similar, and you see that there is a one-to-one correspondence. So you have this x12 that is the same of this, and you can check that all the powers are the same. And I wish I knew why we have this structure, but we don't know. We just observe that this is what comes out of the solution. So there must be a deeper story. We are just brute forcing the results, but there must be another symmetry that should force you and suggest that this is the right structure.
Why is it natural to form a cross ratio of the capital X's?
It's not at the moment. We just find that this combination inside the function f solves the constraint. So we don't understand why, and later I will show that it satisfies some identities that are typical of the cross ratios. So for example, if you take 1 minus this cross ratio, this generalized cross ratio in terms of capital X's, you get another cross ratio in capital X's.
But xij, since it's a function only of of x and z without indices, does not itself transform under conformal transformation of the x's, or does it?
So if you start swapping the xi's, it transforms, but that's the stupid transformation of global word identities. Yeah. Now, if you don't do that and keep the insertion point to be 0, 1, and infinity, and ask, why did you choose this cross ratio, not another one?
Yeah.
Then the behavior that you would usually have in the top formula, you also have in the formula downstairs. So it has some properties of cross ratios, not all of them, because of course, capital Xij is not just something with I index minus something with J index. Yes?
Does the big Xij reduce the small Xij at small separations?
Okay, that's a hard question because we don't really understand what. So you're essentially asking about the space-time OPE, xi being close to xj, from the point of view of the worldsheet. And this is one of the things we don't really understand. I mean, if you want the formula that I will present, and I need a couple more steps for generic spectral flow, reduces to
if you set all the spectral flows to 0, reduces to the correlator with 0 spectral flow. So there is no special, I mean, the case where you have some spectral flows being 0 is a smooth special case of the generic formula.
If I understood correctly, the little x was the coordinates on the boundary of AdS.
Yes.
So you would expect there to be an OPE.
Yes, I agree. That from the point of view of the boundary CFT, the coordinate there will be x, xi, and xj, and being a CFT, there should be an OPE. I agree, but we don't understand how this is captured from the bulk, and in particular from the worldsheet CFT.
So if I set little xi equal to little xj, does the corresponding big xij go to 0?
I think not.
What do I need to do to make a big xij go to 0?
I will come to this towards the end, because that's exactly the right question to understand when these correlators vanish or explode, because indeed you see that this xi12 is raised to some power of the spins. So if the x12 goes to 0, you will have a singularity. And this will be encapsulated again by covering maps. That's exactly the question that I'm going to ask towards the end of the talk, because this will tell us where poles of these correlators sit. But now you should ask me, how do you define these xij's? So I've been talking 10 minutes about them, but I didn't give you a definition. So the red box is the same equation. I just want not to lose it. And I could give you the closed form formula for these xij's, but then we spend 10 minutes decoding what it means. So let me give just examples. So you can actually define these xij's for any subset of 1, 2, 3, 4. And if you have the empty set, this is just the polynomial that I was introducing before, encapsulating the existence of a covering map. And if instead you say pick x1, 2, this will be a linear combination of y1 and y2. So we have a term where there is no y, a term with y1, a term with y2, and a term with both. So it's a linear combination of the auxiliary variables, and the coefficients in front are again these p, w, x, z polynomials, but now you start playing with the ramification indices, and if you put no y, you raise up the associated ramification indices,
And when you put the y, you raise it down. And you have all the combinations.
So are the x's obstructions to the existence of covering maps and more variables?
So, sorry, by more variables, you mean more than 4 insertion points?
No, I mean involving also the y's.
No, so again, this PW of XZ does not depend on W. And when it is 0, it means that a covering map with the associated WIs does exist.
I know, I'm asking if the x's have a similar interpretation as obstructions to existence of covering maps, even though that you've taken linear combinations.
I don't know. Yeah, I don't know of that. I mean, again, we find this just experimentally. We see that this is the nice combination that somehow, I mean, the way we come to this answer, now I show you the complete answer. But the first thing we understand that there is something that has to be raised to these powers, which are linear combination of JIs. And then we find some polynomials that we see they are always linear in Y1 and Y2. Then we stare at what is the dependence in front. It's again a polynomial in X and Z. And experimentally, we find that they are related to covering maps. But Y is not yet clear.
As a function of Z, though, it's more like some map, some embedding of the worldsheet sphere into P1 cross P1 rather than a single dot, because there's X and Y. It's like you're trying to map the worldsheet into some kind of S2 cross S2 rather than just S2.
Yeah, it's not just
It's
one.
not clear what the geometric is.
Yeah, that's related to
There
the
should be
fact.
some geometric
Yeah, you would think.
Yeah, we miss the geometry,
Yeah.
essentially. So all this is algebraic, and we don't really understand the geometry that is behind that is part of the story and probably would give a better picture. Okay, but I promised you a closed formula, and this is not yet it, right? Because we have an unknown function f. So I haven't told you what the function f is, because at this stage it's not fixed. Can we constrain it further? Yes, because we have still one more bullet to shoot. And this is the so-called Knizzitz homological equation. So this is the statement that the translation operator on the worldsheet, so what you would call d by dz, is actually the -1 mode of the Irasoro algebra. And this can be written as a bilinear in the currents. Okay? But we do know the OP of the currents with V. So we know the right-hand side because then we know the action of the J's on V. And we know the left-hand side because it's just a derivative. So we know both sides. So we can insert this equation inside the correlation function. And this will turn into a differential equation, which is a partial differential equation in X and Z. Now, we impose this differential equation on the solution that was in the red box in the slide before. And this imposes a differential equation on the unknown function f. And the first surprise that we see is that the differential equation for the unknown function f does not depend on the wi's. So in principle, I wrote unknown function f, but I should denote as f of 1, w1, w2, w3, w4. It could be a different function for any choice of w's, but it's actually always the same function. So the dependence of w goes away when you impose this differential equation, which implies a differential equation for f. And then we try to solve this differential equation for the unknown function f, but we couldn't. So when you cannot solve a differential equation, you search in the literature if someone before you encountered the same. And indeed, this is the case because the differential equation for the unknown function f is the Knizzitz homological equation that a correlator with no spectral flow would satisfy. And the picture is very similar if you consider null vectors. So if you take a null vector with spectral flow, this will give it a differential equation for the full correlation function that reduces to a differential equation for the unknown function f. And you find that this is exactly the null vector equation that a correlator with no spectral flow should satisfy. So we believe that this is pointing, and this is saying that the unknown function f is the unflowed correlator. I mean, they solve the same Knizzitz homological equation for many different choices of w, and they solve all the same null vector equations. So we believe that this is enough. So the unknown function f is the unflowed correlator. So our final formula is the one on the screen. And I know it looks ugly, but now if we stare at every line, you know what every ingredient looks like. So the left-hand side is the aim of this talk. So computing the 4-point function with 4 vertex operator with arbitrary spectral flow. And the right-hand side is the result. So we have these generalized differences that are functions of the auxiliary variables and encapsulate this polynomial related to covering maps. And then we had some unknown function, but we claim that actually this function is known, it's just the correlator with no spectral flow. And all these nice form we could get in this auxiliary basis of the yi's, but we prefer the usual base in terms of h, so we just have to Fourier integral transform back. And this is what the integral in the first line achieves. So by now we know all the ingredients of this formula, and you see that every property of the correlator with no spectral flow you can translate to a corresponding property of the correlator that does have spectral flow. And the correlator with no spectral flow has been studied a lot, so we know many things about it. It's related to Liouville theory, and essentially any of these correlators you can rewrite in terms of Liouville theory correlators.
Does the KZ equation have a kernel? Like, is this is not the unique possible answer, or is it?
Yeah, it's not. That's why we say that it's a conjecture, because it sounds natural, but there might be other solutions. Yeah, I mean, it's a PDE, so we cannot really claim that. Certainly this is a solution, but we cannot claim it's the unique one. So, but on the other hand, okay, this is slightly technical, but if you go to the case of the 3-point function, and there is another symmetry I didn't talk to you about, it's a bit technical, but I think people in the audience more or less know. So actually, if you consider representations with spectral flow W and W+1, they are related, and it's something like this, that a discrete representation that is highest weight state with spin J and spectral flow W is the same as a representation of the D minus with W+1 and spin K halves minus J, something like this. I mean, the numbers are not precise, but this means that W and W+1 are related. And so you can relate the formula in the case of, say, 1, 0, 0 to the formula with 0, 0, 0, and you see that the normalization, because in the 3-point function this would only amount to a normalization, indeed is the 3-point function. So it's not really a proof, but it's pointing into this direction.
Remind me, the W's are all non-negative?
Yes, the W's are all positive, and non-negative.
And
0 or positive
I mean,
integers.
you can ask about a situation where some are positive and some are negative.
Yeah, so this is, I think, a confusion between this x basis, where we have this x variable, and the so-called m basis, where we don't look at the dependence on x. And usually in the m basis, so when you consider, say, the states in your representation, you would have states with positive and negative spectral flow, and you would say that the states with positive spectral flow are in states, and the states with negative spectral flow, they are out states, or something like this. So you would, in a correlation function, when you have the z at an ordinary point, you would put positive spectral flow, and when you have it at infinity, you would put with negative spectral flow. But now we are in the x basis. And this x dependence also has the complete global world identities in space-time. So it encapsulates both the dependence of x and 1 over x. So in a sense, it has all, it has the behavior both at 0 and infinity. They are just related by global world identities. So we just need the positive spectral flow.
And where is this fact that the winding violation is only up to n-3 units?
Yeah, so we also explained this. So usually okay, you might claim you're not the first to compute this 4-point function. We knew 10 years ago. What we are computing is something different. So before people were, so my correlator, you see that depends on some x and z. Now, people before were computing correlators where there was no dependent on x, which means that is the same of my formula, but with all the x's set to 0 or infinity. So we show that if you set all the x's either to 0 or infinity and have positive spectral flow for those at 0 and negative for those at infinity, you recover what people computed before. And in that setup where you have no x dependence, there is this rule that the sum of the spectral flow can be violated at most by 2 in 4-point functions and by 1 in 3-point functions. But this is a more restrictive scenario because it's the case where these xi's, they are either 0 or infinity. And you see that from the point of view of the space-time theory, so if you are just interested in 2D CFT and you want to solve this model because it's an interest in non-rational CFT, fine. But if you are interested in holography from the boundary CFT, it doesn't make sense that you have all vertex operators sitting all at 0. So you should have them at generic
I understand that. My question, I think, in your language is, how are these? We can talk about it later if you have stuff to talk about. But
yeah, I mean,
my question is not all of what you said. It's more
how
are the operators as a function of x with w defined? Because if you try to write some formal series, I mean, part of the problem is that these operators are winding. Like there's some issue.
Yes, I mean,
local operators.
I agree that I don't.
Which is what you wrote there.
Yes.
Well, I mean, we can talk about it separately.
Okay.
I don't think it's for.
I mean, there is a lot to say, so maybe let's postpone.
Okay.
But yes, this is an interesting point.
But do I infer from your answer, you're saying that these rules that people had developed for these special correlators where all the x's are 0 and 3, those do not apply when x's are generic?
Yes, the rule, if you ask when does a correlator vanish,
yeah,
the answer differs if you consider this x or not.
Okay, so when the x's are generic, what's the rule?
I don't remember exactly, but it's something like that the sum of the wi's should be bigger than the maximum of the w's plus some offset.
So is it related to the degree of the map that you were talking about earlier?
It's not it is and not, meaning that the rule for when these correlators vanish is not a function of the degree, but both the degree and this rule are written in terms of wi's. So they are related, but not in a clear sense. I mean, not directly.
And your formula in the red box is valid universally irrespective of whether the j's are in the continuous or the discrete series?
No. Okay, let me be more precise. This, literally speaking, as it is written, is only for the continuous j's. Now, what you should do for picking up the discrete series, you have two choices which are actually equivalent. So the one is, instead of integrating over the full complex plane of the yi's, you take a contour integral around 0 for the d plus or around infinity for the d minus. Equivalently, you can just integrate over the whole complex plane, but then you need to take residues into the hi's. And this is this LSZ poles, essentially, story that was understood way before we came. Okay. So literally is only for continuous, but there is a clear procedure on how to twist this formula for discrete case. Now, there are a few things you should complain about for this formula. So, for example, it's not clear. So, on the left-hand side, I have some bosonic operators. So, if I swap all the 1 labels with the 2 labels, it's like commuting 2 vertex operators, and they are bosonic, they are local, nothing should change. But it's not clear that 1 and 2 labels play the same role in this formula, and especially the 4th one that has this generalized cross ratio. So this is not manifest, but indeed we check that we do have this bosonic exchange symmetry. So if you swap, they are indeed the same thing, despite it's not manifest. And then you also have, for continuous representation, this reflection symmetry. So J and 1 minus J actually label the same continuous representation, and this is not manifest from our formula, but again, the reflection symmetry of the correlator with spectral flow implies reflection symmetry of our formula. And then we should recover the few cases that were computed before our work, and indeed our formula matches with them. And many of these checks rely on mathematical identities that we cannot prove mathematically rigorously, so we don't have a first principle proof, but we can test very well in Mathematica, and we are confident they are correct. But we, to the best of our knowledge, these identities are not known in the math literature, and they are identities between these PWs with different values of the spectral flow up and down. And for example, one nice identity is this one that I was describing before. So 1 minus this generalized cross ratio gives another generalized cross ratio. And this is what makes the role of 1 versus 2 not special, because they have the same behavior that usual CFT correlators have with respect to global symmetries. Okay, now that we have an explicit formula, we might have some reward, because we can start analyzing what is the physics, more than the physics, what are the properties that this formula dictates. And in particular, we can look when we have singularities, when we have branch cuts, and when we have poles. And now I should talk quickly about some recent proposals that also some people in the audience were working at. So now I want to describe something similar that was done by Lawrence and Matthias a few years ago. So it shares many similarities. So we are, this is the proposal for a dual CFT of AdS3 cross X, where X is an internal CFT, which is unitary, compact, and that has the right central charge, so that AdS3 cross X is a critical string theory. And the value of the string tension, the K, is generic. And the proposal is that the boundary CFT is the symmetric orbifold of some linear dilaton with a specific slope times X, the internal CFT. And this you should deform by a non-normalizable operator that is in the twist 2 sector and has this exponential dependence on the linear dilaton. And in this map, the momentum of the linear dilaton is mapped to the SL2R spin. So there are many other features and many other points we might discuss, but these are all that I need essentially for what I'm going to say. And actually, there was also an analysis of where the poles are for correlation functions computed in this putative boundary theory, and is similar to Liouville theory. So when the sum of the momenta are equal the background charge, or the background charge up to some integers, you encounter a pole in the correlator of the boundary theory. And now you can rewrite these P's in terms of the J's on the worldsheet. So this is predicting poles in these locations. And you have actually to pay a bit of attention, because that's not the only restriction. You also have that from the Riemann-Hurwitz formula that is playing a lot, it's present here because we have symmetric orbifolds and covering maps. You have to impose also that is integer L that parameterizes the ordering conformal perturbation theory is equal to sum of the WI mod 2. This just comes from here. Then you know that the degree of the covering map has to be bigger than the highest W. And this imposes these other constraints. So we find poles at these locations with these two restrictions. Okay, so this is what the boundary CFT predicts. Now let's come back to our bulk theory and analyze where singularities sit. So you have the usual singularities when two vertex operators collide. So when X is close to 0, 1, or infinity, or similarly for Z, you have the singularities that you have usually in any 2D CFT, but we also find more singularities in the middle of the moduli space. And these are located again, so if you think, let's fix X, the value of Z for which we encounter a branch cut in our formula is encapsulated again by these PWs. And they can again shift it up or down. Now, we believe that the physics behind this phenomenon is what Baldacchino and Noburi called worldsheet instantons. So essentially, when PW is 0, it means that the covering map from the worldsheet to the boundary exists. So this means that the worldsheet is allowed to cover the boundary. So the worldsheet is allowed to travel all the way to the boundary, have infinite volume, and cover the boundary. So this means in particular that the path integral will diverge, and this divergence is encapsulated into the fact that you have the correlator diverges. And then the shift of plus minus 1 again is the fact that the representation with W and W plus 1, they're actually the same. So if PW equals 0 has a singularity, also PW plus 1 and PW minus 1 should have. So we have nothing to add to this physics explanation. We are just making they just describe this phenomenon for zero spectral flow, and we believe that the same interpretation is correct for generic spectral flow. But what we can do more is that we can compute the correlator, our formula, exactly close to this singularity. So close to this branch cut, we have an explicit formula. And I wanted to include every factor because we have control on every factor of k minus 2 or pi. So what comes out, let me start from the second line. So this is the branch cut that I was mentioned. So this Z gamma is the solution of this equation. So by Z gamma, I parameterize the various solutions of this equation. So this is where the singularity sits. And indeed, I have a branch cut for Z going close to this singularity, essentially by definition of singularity. And then I have some Z and 1 minus Z dependence. In the first line, I have some normalization factors that are I have some gamma functions and I have some reflection coefficients, but you can think of them as just normalization. And then in the third line, I have some covering map values. So the AIs are the Taylor coefficients, the first non-vanishing Taylor coefficient appearing in the Taylor expansion of the covering map, and the pi is product of residues of the covering map. So covering map data is on the third line, and on the last line is a correlator of Liouville theory. Now, if you remember, we have some Z minus Z gamma to some exponent. If I tune, say, this exponent to be minus 1, then the string correlator that comes from integrating over Z, I will be integrating Z to the minus 1. So this gives rise to a divergence, right? So this signals a pole in the string theory correlator. Now, I hope I convinced you that there is a pole in this special case, but you can make a much more systematic discussion and analyze where all the poles arise from for our formula. And the answer that we find is this one. So this is where poles sit. So for any combination of the JIs that has this sum, and for any value non-negative of m and n, you have this combination. Now the formula is slightly more involved because this A has some case-by-case dependence and it can be a half integer between minus 1 and 1 and depends on the sum of WI. But this formula looks very similar to the one that I presented that was the prediction from the boundary CFT. And actually, if you analyze carefully how this A is defined and you take into account these bounds and additional restrictions on the value L that was the order of conformal perturbation theory in the boundary, they are exactly the same. So for each pole in the boundary CFT, there is a corresponding pole in the bulk. So the pole structure is the same. And actually, in some special case, we can also compute the residue at the pole. Not in general, but in some special case we can. And in particular, when the sum of the spins is 5 minus k, we can compute the string answer explicitly. And this is what comes out. And you see there is some Z gamma dependence. And then there is some covering map behavior. And this CS is just the normalization of string path integral that you should include in correlations functions. Now, if you interpret this formula, you realize that these are the linear dilaton correlator piece. And indeed, it's raised to the product of something that only index 1 and something that has only index 4. And indeed, you can check that what is in the exponent here is just P1 times P4, according to the map that was mapping P to J. And here is P2 and P4. So this is really a free boson correlator. And then if you open the literature on symmetric orbifolds, you see that these factors in the second line are exactly the factors that you should include when you have a symmetric orbifold of a SID theory with central charge 6K. So this is exactly the prefactors that enter any symmetric orbifold correlation function with central charge 6K. So when we have these spins, we can match and exactly reproduce the CFT, the boundary CFT correlator, or to be more precise, the residue at the corresponding pole. And there is a precise matching. So let me summarize what we did and conclude. So we provided a full conjectural solution for the SL2R Belzumino-Witten model with arbitrary amount of spectral flow, and any property of the correlator with no spectral flow can be translated in the corresponding property with spectral flow. And these string correlators have an intriguing pole structure, and the location of the poles in the bulk matches with the proposal for the boundary CFT. And we also checked some residues, and this means that for some, we checked the duality for some non-trivial 4-point function exactly in alpha prime. And as I already told you before, there are many things we would like to understand better and that are not yet clear. So it's not clear how the OPE of two of these V's work. So you might ask, why are you paying all this price to compute 4-point functions? Can you just take the OPE of two V's and this will reduce to a 3-point function? So it should be much easier. We don't really know how the OPE of two of these V's that depends both on X and Z really work. And then we are missing the geometric interpretation of this, what the YIs mean, and why do we have these covering maps related? Why should we have covering maps in SL2R? And why do we have this nice structure that looks like global world identities for these capital X's? We actually don't know, and it's probably the physics behind that we are missing. And then one could check further. Now we have a one-to-one correspondence of the location of poles. We could try to match other residues. So it's more involved, but it should be possible in terms of Coulomb gas formalism and so on. And then this is only the bosonic story. There should be an analogous supersymmetric story in terms of RNS. And then you can generalize to other backgrounds. So for example, BTZ, black hole. And you can generalize to higher point correlators and other generalizations. So these are all my questions, but I guess you also have many questions. So maybe now it's your time to ask questions, and I will be here until Wednesday afternoon. So knock at my office, drop me emails, ask me to talk. I'm very happy to interact with you and learn something from you. Thank you very much. Questions?
So these OPs you talked about here between operators and SL2, eventually you want to do them, I guess, in the, because you had some correlators computed in the Y basis. Is that why
Yes.
it's so difficult to go from a 4-point function to read off?
The first difficulty, so usually there is a trivial exercise for, say, compact CFTs that usually we say that 3-point functions and OPEs, they are essentially a synonym, right? Because what you do is that you make an ansatz for your OPE as a sum over intermediate states with some unknown coefficients, and then you insert these ansatz into the 3-point function that you know what it is, and this gives you fixes the coefficients in your 2-point function ansatz. But this works because essentially you have a delta function that kills the sum of these OPE ansatz, and this doesn't happen here. So you still have some integrals, and it's not clear how to go from one to the other. So this should be a stupid exercise usually, but it's not already clear here. And then the other problem is that you have two variables, z and x. Now, in principle, I'm allowed from the worldsheet point of view, x is just some chemical potential, right? If I ignore holography and all that, from the worldsheet, it's just chemical potential. So when z1 goes close to z2, what should I go with x? What should I do with x? Should probably leave free. But the intermediate states, should I integrate over some unknown x? Or so these are the kind of questions we don't really understand.
So in your last part, where you're trying to match to some space-time CFT, so could you go back to the formula with the linear dilaton correlation? Yeah, there. So the space-time CFT is supposed to have some wall that reflects that extends the linear dilaton by some kind of reflecting wall.
Yes.
So in particular, that should imply some kind of relation between correlators with
some reflection symmetry.
Some reflection symmetry.
Agreed.
So does this formula exhibit that reflection symmetry?
So yes, because from the bulk the reflection symmetry is clear.
Yes.
Okay. But the formulation of the CFT, if you don't rely on any matching with the bulk, is not clear that there is reflection symmetry, right? So I agree, this is an open question on how reflection symmetry gets manifest from in the boundary. It's not clear. This formula is reflection symmetric because it is in the bulk and we're matching. But I'm really exploiting the matching to claim that it's reflection symmetric. So it's not something that I can directly learn from the boundary. When I do this match, now you can do the same manipulations that you do on the bulk. But I agree, this is it's missing our understanding of the boundary theory. So the boundary theory seems to know less despite being more simple. So here we had to pay a lot of computations price to get to a relatively simple formula, right? On the other hand, in the boundary is much quicker to get this formula, but it knows less, so it doesn't know, for example, this reflection symmetry.
Let's thank Andrea again.